sine of infinity. That's telling you, that's basically asking you, what does the sine function do as you go to infinity? That limit in Cal 1 did not exist. Right? If you look at that, you say, hey, here's a sine curve. Go this way. Where is it headed? Is it headed to a number? It's not. It's oscillating, right? So this limit right here does not exist. dne does not exist. That means this integral diverges. All right? So the answer to this would be that this diverges. So diverges does not mean infinite. Now, if your answer is infinity, it diverges. But you don't need infinity for it to diverge. Does that make sense? All right. Did I turn my thing back on? Yes. All right. All right, let's look at the next example. Run over. See the big difference on this one? Going from negative infinity to infinity instead. Now, let's check for those discontinuities. Do we have any? Is there anywhere where this is going to have a problem? Can you make that denominator 0? You're never going to be able to make that denominator 0 unless I allow you to use I, the imaginary number. Right? You can't make this be 0. So we don't have any discontinuities. By the way, just FYI, this is what this one looks like. What's the value of that function at 0? 1? And what happens is out to the right it dives down, and out to the left it dives down like this. So we're trying to find the area in here. Kind of looks like a bell curve, but it's not. It's not the bell curve you're thinking of, if you know what I'm talking about. Okay? Pardon?
You rename both of these.
Do I need them?
No, rename.
Rename them? Sorry, I didn't.
Normally you have like a number on the bottom.
Yes.
And then you put that infinity T.
Yes, you use T. Now, since we have two infinities, we're going to have to basically do that twice.
That's what I'm asking.
Yes, yes. And the question is, are we going to use the same letter? Like, are we going to use T for both? So I don't, but we'll see. Okay, first break it into two integrals, though. So first thing I'm going to do is this. I'm going to rewrite this as the integral from negative infinity to any number I want, 0, of 1 over 1 plus x squared dx, and then plus the integral from 0 to infinity of 1 over 1 plus x squared. This is not an optional step, okay? You must split that into two. Now, for the first one, we have not done one like this yet, right? Where we go to negative infinity. So here's how we write it. We take the limit as t goes to, this time, negative infinity, integral t to 0 of 1 over 1 plus x squared dx. Right? See what I did? I replaced the negative infinity with t, and I'm going to let t go to negative infinity. Plus, now another limit, different limit, and I'm not going to use t again. Use any letter you want. I'm going to use r. I'm going to let r go where? Positive infinity. Integral where to where? 0 to r. Notice whenever I say this, when I say integral from blah to blah, I'm always going from the bottom to the top. Because it's like we're reading it from left to right in a book, like on the number line. So when I say we're taking the limit from 0 to r, that's the way it would appear on the number line. And then 1 over 1 plus x squared dx. All right, now what? Antiderivatives time. Any idea how you're going to integrate 1 over 1 plus x squared? Arctangent. That's arctangent, right? That's arctangent. So hopefully you recognize that as arctan. So we're going to go directly to the formula. So we're going to have limit t goes to negative infinity. I write down the antiderivative, which was arctangent of x. I put a bar here, and I put t down here, and I put 0 there. Over here, I'm going to have the same exact thing. Plus limit, r goes to infinity, and then arctangent of x, and then a bar, but this time 0 to r. Now for each one of these, I've got to, like plug in 0, then plug in t. And then over here, I've got to plug in r and then plug in 0, right? And that's going to give me like 2 sets of parentheses for each one, and I'm going to use some brackets. So I realize that this gets a little tedious to write all this down, and you're using up quite a bit of room on your paper, and you love trees and you don't want trees to die, but they're going to be okay. So I'm writing it down. Here's my 2 parentheses. I'm doing 0 in here first, and then I'm doing arctangent of what? T. So that's my first one, right? Plus, now another limit. This time r is going to infinity, bracket, 2 sets of parentheses, and then I'm plugging in the r first, arctangent of r, and then over here I'm plugging in arctangent of, let's see, 0. Any questions? All right. Now, I want to talk about this because my other class, we got kind of hung up at this point. So let's talk about inverse trig functions, which is something we covered in the very beginning, but it's worth talking about again. If I say to you, what is arctangent of 1? Right? If I ask you, what is that? Then that is the same as me asking you, tangent of what is 1? It's the same question. So it's saying, at what angle is your tangent 1? That's what that is asking you. So you can go back to your unit circle. Tangent is the ratio of your y over your x. Where is that 1? Pi over 4. Happens right here, pi over 4. So the answer to this would be pi over 4, right? Agreed? All right. So let's do these arctans of 0. What is arctan of 0? So that means tangent of what angle is 0? So where is your y divided by your x 0? Right here. That's the 0.10, right? So if you go y divided by x, 0 divided by 1, you get 0. Now another way to look at this would be if you just knew what the graph of tangent looked like. Tangent looks like this. And so I think if you look at that, it's kind of easy to see where it's 0. It happens right here at 0. Right? By the way, where do these happen? We have those vertical asymptotes. Pi over 2 and negative pi over 2. Right?
So does that mean like that doesn't count?
What doesn't? Yeah, this right here, this all turns into 0, right? And this one right here turns into 0. So again, I'm not going to worry about paper or the planet. Yeah, I did. Thank you. This one, thank you. That's what they're called. Curly brace, yes. Yep. And these are called angled brackets. Hey, just the messenger. Okay, so this just is arctangent of what? T? Oh, wait, forgot the minus in front. You still have a minus. Arctangent T. And then I have plus limit as r goes to infinity of arctangent of r. Right? Does it equal negative infinity? Is that what you're asking?
Well, like the sign doesn't exist. It's not like the same thing.
Well, it's not. That's why I wanted to talk about this a little bit first. Let's think about what this is saying. Take a look at just this piece right here. Forget the negative out front, in other words. Just look at this. I'm supposed to replace t with negative infinity, which you can't do, right? You can't plug negative infinity in. But if we're going to do it this way, what would that be saying? It would be saying arctangent of negative infinity equals what, right? That's what that's saying. So that's really saying to you, tangent of what angle is what? Negative infinity. So go back and take a look at your tangent function. At what angle are you negative infinity? At negative pi over 2. See, this is a limit. We're saying as you approach, as your x value approaches negative pi over 2, the tangent function dives down to negative infinity, right? So it's occurring at negative pi over 2. Do y'all see that? So the result of this piece in red is negative pi over 2. Just the part in red. We still have a negative out in front of that. Do you follow me? Now on this one, we're saying, okay, arctangent of r is going to infinity. So what's arctangent of infinity? Well, that's equal to something, right? That means tangent of something must be infinity. So go back over here. Where is your tangent function positive infinity? At pi over 2, right? So you would get pi over 2 here. I'm going to write everything down again. But do you understand the idea? In the limit, that's where it's headed. So I've got now, do I have to write the limit again? No, because I've actually applied the limit now. So I'm getting negative pi over 2, so minus negative pi over 2, plus pi over 2, which is pi over 2 plus pi over 2, which is just pi. The area under that curve in both directions forever is pi. That's kind of interesting.
Does it only work that way with tangent and cotangent? Because they have like...
You could have other functions that do it. Like secant and cosecant have verticals also. Yeah. So, I mean, it just depends. But arctangent's the one we see a lot. All right. We're good? Converges, right? Converges to pi. Fourth one. Do I have any discontinuities? Is that thing ever going to have any issues? X e to the x. Does that ever have any values that I plug in and it just freaks out? E to the 0 is 1. 0 times 1 is 0, so that's okay. I mean, wait, what did I just say? 0 times 1 is 0. Yes. No, you don't have any issues. You don't have any division. There's no, e to the x doesn't have any domain restrictions. Like, that's a well-defined function everywhere. So you don't have any discontinuities. All right, so we can just go right at it. Let me see. I'm going to do two limits again, right? I'm going to let t go to negative infinity of the integral from t to where? Where do you want to go to? Go to 0 again? I like 0. Now I'm going to add to that another limit. R goes to infinity of the integral from 0 to r, x e to the x dx. We all good with that? No questions? Have any issues now? What's your next step? Integrate, right? Integrate. We've got to integrate. And that integral is not as clean as everything I've given you up to this point, right? Like 1 over x squared, we integrated that in our heads. 1 over x, you did that while I was in the hallway, which I assume 1 over x was easy for you. 1 over 1 plus x squared was a formula, so we recognize that, hopefully. This one, I hope I already heard it, integration by parts. So what I would do if I were doing this problem is I would just take a quick little break, and I would come over here and work that problem out. I need to integrate x e to the x. We are going to have the pleasure of your presence today. How you doing, Albino? You doing all right? Good. So, integration by parts. Have to choose a u and a dv. U is x. Y is ux. Yeah, because it'll become a 1 when I do my little du thing. So that's your setup on this. Du is dx. V is the antiderivative of this, which is e to the x. So you see, on a test problem, I could actually ask you something like this and force you to do integration by parts, right? Kill a couple of birds with one stone. This integral becomes ultraviolet minus voodoo. So ultraviolet is u times v, so x e to the x, minus integral of voodoo, which is e to the x dx, which is just e to the x, right? So we have x e to the x minus e to the x, and technically we should say plus c, but this is going to be a definite integral, so that c, we won't need it when we plug it in up here. And if I were doing this problem, which I am, I would factor out an e to the x, just because it would just clean it up. It would make it a little easier when I plug things in if I pull an e to the x out of both of those. All right? Come back over here. Rewrite everything with limits. Limit t approaches negative infinity. I write the antiderivative down, e to the x, parentheses x minus 1. I put a bar out here, t here, 0 here. Then plus another limit. R goes to infinity, and then I write the antiderivative down again, and then another little bar here, 0 to r. You all following what I did there? Now I'm going to have the brackets and the 2 sets of parentheses and the subtraction and all that, so let's do that. Writing down the limit again. Are you tired of writing the limit down yet? 2 sets of parentheses. Then I'm going to have plus another limit, another bracket, 2 sets of parentheses. I'm getting rid of this. One of my colleagues was like, how do you do calculus 2 like in that space? Because we were talking about the camera. I said, I don't know, Newton did it in a shed somewhere, right? Newton developed calculus on his own in a shed, so I think I can do it.
You just have to erase off.
Yeah, I just have to erase a lot. All right, let's plug in. 0 first, right? So 0 into here, e to the 0, e to the 0, e to the 0. 1, okay, 1 times 0 minus 1 minus 1. So, yeah, that's right. I have a 1 here, and then that turns out to be negative 1. So this is going to be 1 times negative 1, which is negative 1, right? Then I plug in t. And when I plug in t, well, I can't really do anything. E to the t, t minus 1. Got lots of parentheses there, don't I? How about over here? Plug in r. So e to the r, r minus 1. Who is that? Is that you? Oh, you're charging over there. Is that like an LED cable? All right, now you plug in 0. And when we plug in 0, we should get the same thing we did over there, right? 1 times negative 1. All right, I'm going to write everything down on a new line. Have we talked about my recycling theory? You know, because we're having to use quite a bit of paper here. Have I told you all about my recycling theory? No? We talked about it. Did I ever talk about it in my Cal 1 class? Recycling? Y'all remember me talking about that?